Welcome for this program. At NCTS, we look forward to disseminate information in all respects of the foundry technology. We always feel that what is there much into the non-ferrous aluminum melting and all, because we deal with the higher temperatures. It is hard is 600, 650 degrees. But the critical part lies there only. The very criticality is there. What will happen if it is below 630? What will happen if it is 20 degrees more than that? And that portion is normally not as critical as the ferrous alloys. Rather, it is not as all that way critical in the ferrous alloys as it is so much critical for the non-ferrous, especially for the aluminum. Even a little higher temperature, tapping temperature makes the difference. And that is what exactly we look forward when we think of the aluminum melting practices or the melting practices and the treatment. Treatment is also equally important for the non-ferrous. You are already aware of it. Because along with the treatment, it's not the treatment what you have with the exact chloroethane and all what you used to have. Because environment problems and then so many things are there. Now the technologies have changed totally. There are newer technologies coming every day. And today's faculty is very well acquainted with those technologies. And then along with those technologies, you need to maintain some protocols of the entire process from melting, efficient melting, energy efficient melting, to the treatment protocols and the pouring protocols. So it's a really all of a very tough gambit, I can say, to make the non-ferrous castings. And I look forward uh, for today's lecture from Mr. Baum that he will make it simplified for us. And I request Mr. Baum to please elaborate us on the subject. Mr. Baum, please.
So friends, we are seeing here a mold box being molded, and this is a gravity die casting. This is low pressure die casting. And now this is pressure die casting or HPDC. Everybody knows that to get a liquid, one must melt it by energy input. This energy can be delivered by electricity using resistance or induction, or by combustion of any fuel like coke, gas, or oil. What are the principles of aluminum melting? Melt the metal as quickly as possible, melt the metal within minimum energy inputs, achieve complete solution, melt it clean, keep it gas free, and minimize the melting loss. Let us go through the melting equipment briefly. There are two types of furnaces. First is direct heating furnaces, wherein we have Sklener furnace or rotary furnace. Second is indirect heating furnaces, wherein we have fixed crucible type, lift-off crucible type, or tilting crucible type furnaces. What are the advantages of direct heating? It gives bulk metal in a very less time. These are fast melting or quick melting furnaces. Since there is no medium or there is no pot in between the flame and metal, the fuel consumption is less. Since the temperatures are of a higher degree, alloying happens very quickly. But simultaneously, what are the disadvantages? Due to direct impingement of flame on the metal, the melting loss is high, oxide generation is high, and these oxides are embedded into the metal, forming inclusions in the casting. Secondly, high temperature on the top side of the furnace, we lose a lot of nucleation, loss of volatile material like magnesium or zinc, and poor control on temperature. In case of Sklener furnaces or chamber type furnaces, from the top layer to the bottom layer of the furnace, there is a temperature difference of about 50 degrees Celsius, which is very severe. As against in case of electric heating, we can melt the metal by induction melting or resistance melting, and we can hold the metal in a resistance heating furnace. Advantages of induction or characteristics of induction melting are fast melting, good alloying, but due to its rapid churning, more and more aluminum gets exposed to atmosphere, hence gas pickup is very high. Secondly, due to corrosive action of fluxes and chemicals, treatment chemicals on the lining, you need a separate holding furnace for metal treatment. You cannot treat the metal in the induction furnace. Next is resistance heating. Due to saturation of resistance coils, there is a limit on size of the resistance heating furnaces, but it gives a slow melting and precise control on temperature. I have seen furnaces which can control liquid metal within plus or minus 2 degrees Celsius, and such control is really required for aerospace grade castings. Secondly, melting cum holding can be achieved in the same furnace because all these furnaces are crucible type furnaces, and crucibles are that way inert or less reactive to the treatment chemicals. And naturally, treatment is available in the same furnace. You don't need a separate furnace for treatment. Now, a brief about melting loss. Since aluminum is a precious material, melting loss governs the profitability of your foundry. Hence, naturally, all foundries have to minimize their melting losses. Aluminum is placed very high in the galvanic series, and hence it oxidizes rapidly, rather instantaneously. Once you remove the oxide film on the top of molten aluminum, immediately it is replaced by a fresh oxide film. And this process never stops. This oxide film, if disturbed or punctured or submerged in the liquid metal during tapping or during pouring, it folds, it crumples, it folds and forms a bifilm. And such bifilm inclusions or bifilm oxides are very difficult to remove because these are very tiny fragments. हम अगर इसकी तुलना दूध के साथ करेंगे तो दूध जब हम उबालते हैं तो बहुत पतली मलाई शुरुआत में आती है. अगर इसी वक्त वो पतली मलाई तोड़ी जाए या दूध को हिलाया जाए तो पतली मलाई के छोटे छोटे टुकड़े ऊपर से लेकर नीचे तक दूध में फैल जाते हैं. कुछ इसी प्रकार से ये एल्यूमिनियम की जो पतली मलाई होती है, ये थिन फिल्म जो होती है, ये जब हम तोड़ते हैं डाबू डाल के, लैडर डाल के, कोई भी चीज डाल के बेल आउट करने के लिए, जैसे ही हम लिक्विड में कोई चीज इमर्स करेंगे, ये ऑक्साइड की फिल्म टूट जाएगी और हमारे वेसल के साथ, हमारे पॉट के साथ वो मेटल में नीचे चली जाएगी. और ऐसा हर बार होगा तो लॉट ऑफ ऑक्साइड गेट्स एम्बेडेड इनटू द लिक्विड मेटल and it becomes a challenge to clean this oxide during metal treatment. Unlike ferrous metals or other non-ferrous materials like copper alloys, the density of aluminum oxide is comparable to that of molten aluminum. In case of iron or in case of copper, all the oxides float on the surface of molten metal very quickly. But since aluminum oxide has got comparable density with liquid aluminum, it does not float that easily. And hence, it is difficult and a lot of flux is to be used, a lot of time is wasted in cleaning the metal. And hence, during melting, if we use covering flux very properly, we can reduce this melting loss. I have seen foundries with melting loss up to 10%. But practically you can control it to as low as 2%. And if your workers and supervisors are trained, their skill set is upgraded, it can be further controlled to less than 1%. And we know that aluminum is an expensive material. Roughly you can say it at 150 rupees a kg. So you can just imagine from 10% to 2%, it's a 8% reduction, and that is addition of about 12 rupees to your kitty directly. Now, how can we control melting loss? Melt and hold at the lowest temperature in shortest time. Do not hold metal for a long time. Consume the metal in shortest time available. Cover the metal by cover flux to prevent air contact. Do not disturb the oxide film once formed. Dispense the metal in shortest time with least exposure to air. Now, we should know that to have a good quality of casting, we must have good quality of liquid metal. Any molten metal has got many unwanted parameters which have to be corrected in order to get desired effects. Remember one thing, all the mechanical properties which we try to achieve in the casting or in the test bar, these properties take birth during metal treatment itself, and further they are enhanced during solidification. So to get correct quality of material, correct quality of casting, we have to correct the liquid metal. The process of correcting this dirty metal is called as metal treatment. Now one will say that I am using pure virgin ingots. Those are already pure. So why do I need metal treatment once again? Because like we have seen, it oxidizes very rapidly, very easily, and hence that oxide itself we have to remove. Secondly, the furnace atmosphere or the ambient, the air near the furnace, that itself has got moisture. That moisture is nothing but H2O. At elevated temperature, the molecule of H2O fragments and hydrogen and oxygen are separated. The hydrogen dissolves in molten metal and oxygen oxidizes the molten metal. So howsoever pure your ingots may be, unless and until you are into vacuum melting furnace, your metal is going to get dirty during melting itself. Now why to treat this metal? First is to remove dirt or inclusions. Second is to eliminate dissolved gases. Third is to nucleate metal for better solidification. And fourth is to improve microstructure of eutectic silicon. There is a typical sequence of metal treatment. This sequence has to be followed if a foundry is using chlorine or chlorine emitting substances like hexachloroethane tablet for degassing process. Initially, we have to clean the metal, which is called as cleaning or cleansing. Second, we have to degas the metal. Then next, third in line is grain refinement. And last is modification. This sequence has to be followed if we are using chlorine or hexachloroethane. This sequence can be changed, or cleaning has to become first in any case, but degassing, grain refinement and modification can be performed simultaneously if we are degassing using an inert gas like nitrogen or argon. Now let us see the individual metal treatment processes. The first of it is cleaning or cleansing. We understand that aluminium gets oxidized to 2 to 5% or maybe 10% in some cases. This process is always going on till the metal is liquid. The aluminum oxide is spongy porous in nature. It's like a sponge and or a mop or a sponge, just like it absorbs water. This sponge of aluminum oxide absorbs liquid aluminum, and hence it remains suspended throughout the depth of the liquid metal from top to bottom. This is how the spongy oxide looks. Now, if we try to break it, we can find that we have we have got aluminum embedded within that sponge. And this is an evidence that just like our kitchen mop or kitchen sponge absorbs water, the spongy oxide of aluminum absorbs aluminium. Aluminum oxide, very rich in aluminium, is in lumpy form. Whenever I go to any of my client foundry or shop floor, my first visit is to the dross bin, wherein the aluminum oxide or aluminum dross is being collected during metal treatment. If the dross is very light and just like a sand, you can move it very easily, then the melting practices are under control. But if you find such a lumpy dross, a heap of lumpy dross which is like hard metal, then the foundry practices are very bad and they need correction. Such a foundry having lumpy oxide lumps or lumpy oxide cannot deliver good quality castings, and also it incurs heavy melting losses. Now we will be seeing what is called as oxide inclusions. These dark patches are nothing but aluminum oxides, and these thin lines, thin but dark lines, are biofilms of aluminum. Now here in a further expanded view, you can see clearly a biofilm oxide inclusion embedded within aluminum. Under microscope, the similar biofilm inclusion can be seen. This is a fracture of a test bar. On this right hand side, you can see a triangle, a dark grayish or blackish triangle. This is nothing but an oxide lump. Coverall fluxes or cleaning fluxes are usually mixtures of sodium chloride, sodium fluoride, potassium chloride, cravelite, etc. Every manufacturer has got their proprietary mixture for specific application, and hence the manufacturer has authority to recommend the percentage or dosage of use. These fluxes break the spongy network, and due to exothermic reaction, the embedded metal expands and drips down from the sponge, and the liquid droplet merges with the molten metal, and a part of this flux has formed a liquid flux cover, just like a thick viscous liquid on the top of your molten aluminum. The broken fragments of this spongy network of oxide get embedded in that liquid flux, and hence it becomes very easy to clean the metal. This is a video. The operator is putting the required amount of cleaning flux. After a while, he churning the metal. Why this churning is necessary? Because we have understood the aluminum oxide is right from top to bottom. The flux has to come in contact with maximum amount of aluminum oxide. And now you can see that the oxide which he is throwing out is in powder form. It is not lumpy oxide. This is how the oxide should look. Aluminum oxide taken out from the crucible has to be in powdery form. It's a light gray colored powder. If it is not removed, it leads to inclusions. Being skilled foundrymen, we should possess the quality to predetermine the effectiveness, or what you can say, the quality of liquid metal after metal treatment. If we have performed the cleaning action properly, then the metal has to be free from oxides, or the oxides have to be under control. Before we go for casting, can we predict whether the metal is corrected or not? This is called as predetermination of the quality. Right now we are discussing about the inclusion level. There are three methods of predetermining the inclusion level. First and foremost, which is a practical shop floor test, is K mold. It is nowadays getting popular in Indian foundries. Next is pre-fill PODFA, which is not so common. Hardly 1 or 2 units in India are having this facility. And third is Limca. This is not a popular cold drink Limca. Both these, PODFA and Limca, are short forms or synonyms of processes, which we will understand later. This is how a K mold looks. It's a patented design. This is how a K mold sample looks. It has got 5 notches, and this casting or this sample is cast on an inclined plane. The metal is poured into the preheated mold having 5 notches, and the test sample, like flat bars of size 240 by 36 by 6 mm, are obtained. These test samples need to be broken at the notches and put together as shown in next slide. Next slide has an error. It has only 4 fractures, but if you combine all these 5 notches, then you will have 10 fractures. The fracture surfaces are analyzed either visually or by image analysis under low magnification. Rapid solidification of the sample produces very fine matrix and thus inclusions are clearly detected on the fractured surface. Number of total inclusions noticed divided by the surfaces given. It gives the K value. Now from the 5 notches after fracture we will get 10 surfaces. So under our inspection, if we find that there are 4 dark dots or 4 number of inclusions and from total 10 surfaces, then the K value for this sample will be 4 divided by 10, that is 0.4. Lower the K value, better the metal. If you find 20 dark spots, then the K value will be 2. Now, stretching, this is where the patent document ended. I applied my common sense to this particular phenomenon, and herein observation of a farm irrigation or a storm water drainage alongside the road is very important. You might have noticed that whenever a storm water is flowing in a channel, a lot of dirt, fallen leaves, or anything is floating on the water. Wherever the stream changes its direction, that dirt gets accumulated at that corner. Similarly, in this K mold, the molten metal is changing its stream at 5 notches. So naturally, whatever is the inclusion, it will have a tendency to get accumulated at every direction change, that is at every notch. So larger inclusion will naturally get caught at the first notch itself. Naturally, the flowing metal will be partially purified. It will get rid of at least one inclusion particle. The rest of metal will flow further. If at all there is any further inclusion left, it will get caught in the second notch. If at all any further inclusion is left, it will get caught in the third notch, likewise. Now, if we are able to identify the notches, which is the first notch, which is the second notch, then this extension of common sense can be applied. If you get dots only in the first notch, then your metal is quite pure. And if you get inclusions in all the 5 notches, then the metal is quite dirty. Now the next predetermination method is prefill and portfa put together. In the step 1, measured quantity of molten metal is poured in a measurement cup which is placed on a vacuum chamber, and this whole system is placed on a weighing balance. Once all the metal is poured, the lid is closed, and from the bottom side vacuum is applied. In between the vacuum chamber and at the bottom of measuring cup, there is a pre-calibrated filter with very fine apertures. Molten metal does not flow through this filter unless vacuum is applied. It is so fine. Now after vacuum starts, flow rate begins, and in the data acquisition system, a graph of weight versus time is plotted. Indirectly, it is the flow rate. With every droplet being sucked in the vacuum chamber, whatever inclusions are present in the molten metal, they try to clog the filter. They get settled in the filter itself, and the available cross-sectional area for metal to flow gets reduced. So naturally, the flow rate drops. At some time, the filter clogs totally and metal stops flow. That is where the graph ends. The filter is so designed that howsoever pure the metal may be, it will have some metal left above the filter. So this particular process of plotting the graph is the first half of the predetermination process, which is called as pre-fill. And these graphs are called as pre-fill curves. The whole apparatus is porous disk filtration apparatus or porous disk filtration analysis principle. That is why this name PODFA has arrived. Now, in the PODFA or the later half of the process, this solidified material or this crucible along with the filter is broken. It is sectioned vertically, and that vertical section is observed under microscope along with image analysis. The number of inclusions found above the filter are 10,000 times more than the number of inclusions available in the molten metal. That was the principle of the PhD thesis proven by the scientist. We are not going into theory, but we should remember that after image analysis, if you get a value of 1,000 inclusions uh, per volume of that liquid metal, then naturally in in practice, the total liquid metal will have 10,000 times lesser inclusions. That is, it will have zero point 0.1 inclusion per unit volume of the metal. All these processes, right from K-mold, pre-fill, PODFA, and Limca, are patented processes. So do not try to copy the equipment because it is an infringement of intellectual property. Very clean metal flows quickly, giving a steep straight line, and the area under the graph is quite high. And a dirty metal will saturate very early, the graph will be flat, and the area under the curve will be very small. This is how the prefill curves look. This blue line is an indicator of a good quality of metal. Next is a moderate quality. Next is slightly dirty. And the lowest line is very dirty. This is how the PODFA microstructure looks. Now, why this process is important? Because prefill gives you a shop floor test within 2-3 minutes whether the metal is clear or not, which is good enough. It has direct linkage to the microstructure. But the PODFA micro will take hours and hours, and hence it is called as post-mortem. So both these tests have to be performed simultaneously because prefill gives you a practical indicator and it allows a foundry to go for casting, and PODFA gives you an evidence which can certify the quality of casting. Now next is Limca apparatus or Limca principle. This is also a short form, liquid metal cleanliness analysis, LIMCA. Now principally we can understand that there is a glass tube having a very small aperture at the bottom. That glass tube can be connected to a vacuum pump. It has got an electrode inside. There is already a electrode in the liquid metal, and you dip this glass tube into the liquid metal with vacuum on. The moment liquid metal enters this glass tube being sucked by the vacuum, and the moment it touches the electrode within the glass tube, electric current is established between these two electrodes because aluminium is a good conductor of electricity. Both these electrodes are connected to signal catching equipment or ammeter or maybe a data logger, whatever the case may be. Once the current is established, the logging begins. The aperture is so small that whatever is the oxide, the moment that oxide inclusion passes through that aperture. Now we have to understand that aluminum oxide is an insulator. Although aluminum is a good conductor, aluminum oxide is an insulator. Hence, the diameter of the orifice or the diameter of the small hole is the cross section of the conductor area, and hence the moment any oxide particle passes through that orifice, it blocks that conductor. The area of conduction reduces, and hence there is a sharp decline in the current. Every time that particle passes or any other particle passes through that orifice, there is a dip in the current, and that is plotted along the time. So this graph gives you a direct count as well as the amplitude of these dips give you an indicator of size of inclusion. It's a beautiful concept, but yet again it is patented. We cannot copy it directly. This is how the equipment looks. Now we move on to second part of metal treatment, that is degassing. Hydrogen gas dissolves in molten aluminum to a great extent, and this gas remains within even after solidification. This leads to a very common defect called as pinhole porosity, which reduces the strength of casting, and also the casting fails for pressure tightness. This is how the pinholes look. And remember one thing, if your molten metal is dirty or gassy, then pinhole porosity will appear all over the liquid metal passage, that is from the pouring basin up to the exit riser. Everywhere you will find pinhole porosity. Let us understand the solubility of hydrogen. At or around the melting or pouring temperature of aluminium, the solubility of hydrogen increases exponentially. From near zero, it reaches to 1.2% within no time, and occasionally it may cross 2%. What is degassing? Removing dissolved hydrogen from molten aluminum is called as degassing. Degassing can be done by immersing tablet emitting chlorine or nitrogen, or passing or purging inert gas like nitrogen or argon. What is the mechanism of hexachloroethane tablets or tablet degassing? Whenever these tablets are dipped in molten metal, this rise in temperature leads to sublimation of the tablet material. And this sublimation is assisted by fragmentation or chemical decomposition of the elements, leaving chlorine or nascent chlorine in gaseous form. This chlorine reacts with dissolved hydrogen and forms hydrochloric acid or HCl gas. And curiously, this HCl does not have any solubility in molten aluminum. Hence, it passes out very quickly. But again, there is a catch in this. HCl is highly reactive with aluminum. Hence, it forms aluminum chloride, which is a highly exothermic reaction. And naturally, during this reaction, HCl again breaks down. The chlorine attaches to aluminum, hydrogen is released, and this hydrogen again finds its place in molten aluminum. So whatever may be the amount of chlorine being used, you can purge pure chlorine gas also, but whenever degassing is done by HCl or by chlorine, you cannot remove hydrogen fully. You can reduce the quantity of hydrogen to acceptable limit, but it cannot eliminate hydrogen. This aluminum chloride is a dark gray colored powder and it increases dross formation and thus metal loss. There is a marketing trick, very popular marketing trick being employed by these flux sellers. They try to tell you or they try to convince the foundrymen that this degassing tablet not only removes hydrogen but it also removes oxide. And as an evidence, they show that if we are using only cover fluxes or cleaning fluxes, in the first lot we removed about 1 spoonful of oxide, and now we are dipping this tablet, and now you can see that there is so much effervescence, bubbling, very rapid reaction is happening. And after that, now when I remove the dross, you can find there are 2 spoonfuls of dross. But friends, understand that the first spoon was of aluminum chloride, rather aluminum oxide, and the second spoon was of aluminum chloride. Whenever you use chlorine for degassing, the color of dross changes from light gray to dark gray. And hence, the dross is removed, which is spontaneously generated. It was not present earlier in the metal. This video shows you the reaction of hexachloroethane tablet or the tablet degassing. You can see the gas coming out, the bubbling. This kind of degassing is injurious to the health of operator as well as it is hazardous to environment. Emission of chlorine is a greenhouse gas and the carbon footprint of chlorine is 21 times larger than that of carbon dioxide. Hence remember, if you are seeking any TS certification, then you cannot go for chlorine or hexachloroethane degassing. What is the advancement or what is a greener and cleaner process of degassing? That is nitrogen degassing or argon degassing, or broadly we can say it's inert gas degassing. There are two ways of inert gas degassing. First is by just purging, wherein bubbles of inert gas are initiated through a lance or a tube immersed within the liquid metal right up to the bottom of the crucible. The effectiveness of this purging can further be increased by putting a porous plug at the end of that lance. Why? Because diameter of bubble is very important for effectiveness of degassing. Larger the bubble diameter, smaller is the surface area available to that volume of gas. So naturally, the area available for reaction with dissolved hydrogen is limited and it catches lesser hydrogen within. Smaller the surface area, smaller the diameter of the bubble, larger is the surface area made available to the predetermined volume of the gas. Hence, it can reach to more and more number of hydrogen bubbles, and hence effectiveness of degassing is increased. Next advancement in it is by rotary degassing, and a short-lived, or you can say it's underexploited or under trial version is nitrogen tablets. This video is of rotary nitrogen degassing. A graphite impeller or graphite rotor is immersed in the crucible or in the treatment ladle. It is rotated at predetermined speed. Nitrogen or argon, any inert gas, is passed through this rotor. This rotor being hollow, you can pass the gas right up to the bottom of the rotor. The rotor creates a vortex within the ladle or the crucible, and the linear velocity at the tip of the rotor breaks the nitrogen bubble to very, very small bubbles. And these bubbles are released in the liquid aluminium, which, while coming up, catch the hydrogen. We have initially seen that if aluminum is molten in induction furnace, due to rapid churning, more and more surface area is exposed to atmosphere, hence we incur high melting loss. Now in case of rotary degassing, we are physically churning the metal. That means we are exposing more and more surface area of metal to atmosphere. So it is very necessary to use proper flux during the rotary degassing process. Usually this degassing cycle lasts for about 10 to 12 or at the most 15 minutes. Popular fluxes being used are coverall fluxes in powder form. Such fluxes lose their effectiveness within 3 to 5 minutes, and hence they do not last for the full cycle of rotary degassing. Hence, granular flux is being used along with rotary degassing. Such a granular flux has a higher bulk density, hence it lasts for a much longer time, usually for 15 to 20 minutes, and hence for the total duration of our rotary degassing, we get a flux cover and an active flux which do not allow any further oxidation, which do not allow any further gassing, and also simultaneously it catches any left out oxide inclusion within the liquid. In the video, you might have noticed that there is a white colored baffle being introduced along with the rotor within liquid. This baffle is very, very important. Why? Because whatever is the oxide and the flux, it is floating on the surface of metal, and if baffle is not in place, that oxide will get caught in the eye of the vortex and will reach to the bottom of crucible once again. Hence, the purpose of putting granular flux will be lost. So in case of rotary degassing, one must use baffle also. This is another video of rotary degassing with baffle and granular flux. Now, can we predetermine hydrogen content? Can we assess the effectiveness of our degassing process? The answer is yes. It can be done by three means. First is visual inspection of solidifying metal surface, which is just an indicator whether the metal has got any gas or not. It does not give you any indication, any hint of the quantity or amount of gas present in it. Next process is quite practical and very fast, very affordable as well, which is density index analysis using reduced pressure apparatus. And the third and more sophisticated version is online gas content measurement. The first method we are observing now. On the solidifying surface, you can see tiny white spots appearing during solidification. Every spot is an indicator of a gas bubble being exploded on the surface. And hence, it is highly subjective test and operator dependent. One operator might see these gas bubbles, other operator might not see these gas bubbles. But yet again, such a test is important because it creates an awareness that we have to test before pouring. Now we are seeing the reduced pressure apparatus. Molten metal is poured in a crucible and the crucible is placed in a partially vacuumized chamber. What is the principle? What happens here? Dissolved gas is in form of a small tiny bubble, a microscopic bubble. When we reduce the pressure of the atmosphere of this sample, a relative pressure is created within that bubble and atmosphere. Just like we inflate any balloon, we create a relative pressure within the balloon and the atmosphere by applying high pressure inside. But here we are doing exactly reverse. We are reducing the pressure at the outside, and the bubble itself is captured at 1 atmosphere. The pressure in the vacuum chamber is far less, which is to the tune of 80 millibar. Hence, this relative pressure makes this bubble expand. Some of these bubbles come to the surface and explode. They are released. But majority of these bubbles are caught within the sample because the sample is getting thick and viscous every minute and eventually it solidifies. All these expanded bubbles within the sample thus increase the volume of the solidified sample. Naturally, the same mass has got a larger volume, hence its density reduces. Another sample of the same metal is simultaneously poured in a cup, which is allowed to solidify in atmospheric pressure. Density of that sample is compared with density of this vacuum sample. And the difference in densities expressed as percentage of the air solidified sample is called as density index. This is how the density is being measured using Archimedes principle. And these equipment give you the index value, density index value directly. These equipments can be coupled to the PC. If a foundry does not want to go for that kind of sophistication for short of capital, then it can form a comparator of its own by using half of this process, which is the reduced pressure apparatus. The sample which you solidify in vacuum or partial vacuum, if it is cut vertically, then you can find such surfaces for variety of gas levels. But then every foundry has to perform an exercise at least once in the life cycle of that equipment, because the degree of vacuum will differ from equipment to equipment as well as from time to time. Hence, for X degree of vacuum, what is the definition or what is the size of bubbles which you see in the section? It has to be verified, and then you can make your own comparator. The last one is online gas determination. There are two equipment, Alspec H and another one is Alscan. Both these equipments are very sophisticated and expensive, but they come very handy because it can be coupled to your automatic degassing unit or metal treatment unit. How it can be coupled? Because these equipment give you online value in ppm of hydrogen. You can program your equipment in such a way that the moment the ppm level rises above some predetermined level, the degassing cycle will start automatically. Since the measurement is online, the moment it drops to the desired level, the degassing cycle will end. Gradually, over a time period, gas pickup will begin again. If you require some gas to be left behind, usually for helium leak-proof castings, you require certain amount of gas being present, or it has to be present. Then you have to gas it again. You can play with the degassing and gassing cycle as per your choice if you have online gas measurement. Now we come to the third process of metal treatment, third part of metal treatment, which is grain refinement. It is nothing but nucleation. When a metal starts to solidify, the wall of casting solidify first and the interior metal solidifies last. As the solidifying front advances, the dendrites grow towards the liquid further deep, and any liquid metal has occupied larger volume because of its thermal expansion. During cooling or during solidification, it loses that heat. Naturally, it has to lose that volume also. So as long as the liquid metal is available on the surface, that volume reduction happens on that surface. But assume a case wherein the top surface also gets solidified and the liquid island is left within the volume of casting or volume of solidifying metal. Then what will happen? From all directions, the solidifying front dendrites will grow. Eventually, they will end up at the center of that liquid pool. What will happen to the volumetric reduction? That reduction will get reflected in form of a cavity or a void at the center of that liquid pool, which is called as shrinkage cavity. For general purpose aluminum alloys, or we can say aluminum 3 series, 365, 348, or like that, from 7 mg up to 12 mg. As a thumb rule, the liquid to solid contraction of aluminum is 6.5%, which is very high figure compared to any other metals. So aluminum is highly prone for shrinkage cavities, and grain refinement or nucleation plays a very, very important role in controlling this shrinkage. In the first case, we saw what happens, that all the shrinkage gets concentrated at the center of the liquid pool because solidifying front is being advanced from all the surface inwards. Now, if we try to nucleate, what is the process of nucleation? We are creating artificially induced solidification sites within the liquid metal itself. We are adding some foreign material which initiates the first dendrite formation, the first solid particle formation, and from there, these particles grow in all directions. Now let us assume a hypothetical figure that in the same liquid pool, we have induced 10,000 such solidification sites. What will happen here? The solidification will begin from the mold wall as well as from these 10,000 sites, and it will grow in all directions. The theory of grain growth says that the moment a dendrite touches adjacent dendrites, its growth stops. So whatever is the shrinkage volume, in the first case, without nucleation, it will be concentrated at a single spot. In the second case, with 10,000 nucleation sites, it will get fragmented or it will get distributed at those 10,000 solidification sites. Hence, if we assume 1000 cc of casting volume, the shrinkage cavity volume in the first case will be 65 cc. In the second case also, it will be 65 cc, but it will not be concentrated at one single location. It will be distributed at 10,000 location. Hence, the nature of shrinkage will become very, very benign. It will be acceptable and the casting will not leak, it will not break. That is the beauty of grain refinement. Again, it has got a direct relationship with the mechanical properties of the casting. How do we check tensile strength or yield strength? It is from a tensile test bar, a test sample of a predetermined cross-sectional area. During ultimate tensile test, we achieve a fracture in that test bar. What happens during fracture? Grains on one side of the fracture, they dissociate from the grains from the other side of the fracture along the grain boundary. This is in metallurgical terms called as slip of grains. And to achieve slip of grain along one single grain boundary, certain amount of energy is required, which is called as slip energy. This slip energy is a characteristic of the alloy system. So whatever is the composition of my alloy right now, the slip energy required to dissociate two number of grains along one grain boundary will be 1 unit. And beauty of this concept is such that the slip energy remains constant irrespective of the size of the grain. So in the first case, we had 4 or 8 grains in the same volume, naturally in the same cross-sectional area. In the second case, we have got 10,000 grains in the same cross-sectional area. Or maybe 10,000 grains in the same volume, maybe some 500 to 1,000 grains in the same cross-sectional area. What will happen? The slip energy demand or the requirement of slip energy required to dissociate those 500 grains will be 500 units. Whereas in the first case, it was only 8 units. So naturally, after grain refinement, the demand of slip energy increases. That is, the load-bearing capacity of the alloy system increases. The sample goes to fracture level at a very, very elevated load. Hence, UTS increases. So this is direct relationship between grain refinement and mechanical properties. Grain refinement can be checked visually by particular kind of etching agents. For visual inspection, Tucker's H, Tucker apostrophe S, is a popular reagent. It's a combination of HCl, HF, HNO3 and H2SO4. You have to immerse a machined surface of aluminium test piece for 20 seconds in that etching agent and then wash it thoroughly. During drying itself, grain structure is revealed and the two photographs are indicator of coarse grain and fine grain. Same can be verified and evidence can be created through image analysis software under microscope. American Society of Materials, ASM, has classified the types of grains. Type 1 grain are supposed to be finest and type 6 grains are supposed to be the coarsest. If you are using the image analysis software, then the software gives you ASTM macro grain size number. Larger the number, finer is the grain, and smaller the number, coarser is the grain. Let us move on to the last part of metal treatment, which is modification. For modification, let us understand the aluminum silicon phase diagram. The eutectic point is at around, whatever you are seeing in the slide is just a small fragment, a small portion of the total phase diagram. Eutectic point is at 12.6%. And these orange, red and blue lines, all these lines are of particular alloy system. This first line is of solid solubility, which is 1.65%. The red line is of ALSI 7 mg alloy or A356 or LM25, what we popularly call as. Next line is ALSI 9 mg. Why these lines are drawn? This is to explain the concept of eutectic silicon. Now this black line from 660 to 574. This slanting line is the solidus. This flat line, horizontal line, sorry, I'm very sorry. This slanting line is the liquidus. This flat horizontal line is the solidus. And the transition in between the liquidus and solidus is the freezing range. What happens if we say that take the case of ALS as 7 mg, this red line? At this particular spot, wherein the red line touches the liquidus, just slightly below the liquidus line, the first alpha particle is formed. From the lever rule, you can calculate the quantity of alpha and quantity of beta. This alpha formation continues till it reaches the solidus line, which is this horizontal line. At this line, all the alpha percentage has solidified and all the beta percentage is still in liquid form. Now, what we understand by solid solubility? In alpha phase, aluminium will retain only 1.65% silicon. Initially, we had 7% silicon in it, out of which 1.65% silicon is absorbed or is retained in alpha phase. Now, for simplicity, let us assume that at this particular stage, we have got 50% alpha and 50% beta. So 50% of the volume of material or 50% of the weight of material has by now solidified, keeping 1.65% of silicon in it and releasing or rejecting the remaining silicon, which is about 5.35% of the weight so far solidified. So 7% silicon in the remaining liquid plus 5.35% silicon rejected by the solidified alpha. It increases the amount of silicon in the remaining beta and eutectic to a very, very great extent. This total eutectic or this total beta phase instantaneously solidifies as soon as you cross the solidus line. And the silicon present in this beta takes its morphology or it takes its shape, size, nomenclature at this particular single degree Celsius. A degree more, it is in liquid phase, it is not visible. A degree less, it is in solid phase, it becomes visible. And eutectic silicon without any treatment is acicular or needle shaped or platelet shaped. Randomly oriented needles or randomly oriented platelets are relatively harmless. But in presence of certain impurities like iron, these needles or these platelets get specifically oriented. They align themselves along the impurity particle. And such a alignment of these needles or these platelets physically separates the metal matrix. On one side, there is soft matrix, on other side there is soft matrix, and in between there is very hard and brittle beta concentrated phase. So such a structure reduces elongation and it may lead to abrupt failure. In contrast, certain elements like sodium, strontium, antimony, phosphorus, bismuth, calcium, etc., if they are added or if they are present in the liquid metal in very small quantity, in traces, they change the nomenclature of the morphology of eutectic silicon. It changes from needle or platelet or a flake to a bundle or to a globule or to a very, very small tiny fragment. This is similar, conceptually similar to what we see from flake graphite to nodular graphite. A similar transformation happens in case of aluminium for silicon. Silicon changes its morphology from a needle or a platelet to a small fragment or a bundle or a globule. This process is called as modification of silicon. Such a small tiny fragment or such a globular shape is more beneficial for strength because it does not form a hard plane in between. Even if impurities like iron are present, this modified silicon, although it coagulates around that impurity, it will still be in globular form, and hence a slip plane will not be created, thereby increasing the elongation of the casting or elongation of the test part. Also, by such tiny fragmentation, response to heat treatment improves very drastically. On the left hand side, you can see the flakes or needles of silicon. This particular one is a large platelet of silicon. And on the right hand side, you can see fine fragments of silicon. This is a fracture or a solidification crack created along the acicular silicon, which gets specifically oriented. Such a fracture cannot happen in finely fragmented or properly modified structure. Again, ASM has classified the types of modification. Type 1 modification is totally unmodified, and type 6 modification is fully modified. So type 1 is fully unmodified. Silicon is present in large plates or acicular particles. Type 2 is lamellar. Silicon is both lamellar and acicular. Type 3 is partial modification, wherein lamellae began to break, acicular silicon still prevails. Type 4 is non-lamellar. Silicon, most lamellae are broken and only few acicular particles remain. Type 5 is modified. Silicon is in fibrous particles, acicular particles are gone. Type 6 is super modified, wherein very fine fibrous structure is seen. In case of critical engineering components, type 3, type 4, type 5 are preferred. In case of aerospace components, type 5 or above are preferred. That's all for aluminum melting and metal treatment.